Hi, deep learning enthusiasts. It's Saturday again, and I do want to send a little apology out to our group. It seems that I know I made the announcement that we're going to be moving this to a weekly discussion, and I updated the spreadsheet, but apparently I forgot to update the meetup page, so that was totally my bad, and I'm sorry about that. I did send out some reminders and some links to different groups to hopefully get some people to join us for the discussion today. But fortunately, this is recorded, so if you can't catch us right now and interact with us live, at least you'll be able to follow up and watch the video on your own time, which is awesome. So still lots of opportunities to learn about this chapter specifically. So I want to give a little intro like I usually do for new people that are just joining us. This specifically is the online discussion of the deep learning book. And here we're going through each chapter 1 week at a time now. And we're actually breaking up the chapters into different sections because the material that's being covered gets a lot more dense. We want to make sure that both the presenters and the audience has an opportunity to get through everything and have a good understanding of what's being covered. So we do have volunteer presenters each week sign up on our presenter sign-up sheet, Google spreadsheet, our meetup group, and also on the YouTube channel below. So if you'd like to be a volunteer presenter, that would be awesome. We really appreciate it. And also, if you want to find us on meetup.com, we're under the Deep Learning Enthusiasts. So please join us there as well. And I'd like to introduce our presenter this week. We have Shafaq Ozkan joining us. Do you want to introduce yourself, Shafaq?
Sure. My name is Shafaq from San Francisco. I'm a freelance data science contractor, and I have a background in computer simulations, including computational fluid dynamics, applied math, and physics.
Shafaq, would you mind speaking a little bit louder? I think.
Oh, really?
Yes, yeah. Thank you.
Is it better?
Yes, that's perfect. Thank you.
Earphone and microphone thing. If that's a problem, please let me know, and I can maybe plug it off. Okay.
Okay, great. So do you want to go ahead and get started? We're doing chapter 7, which is regularization for deep learning.
Correct. Chapter 7 is entitled Regularization for Deep Learning. It entails these subsections. I made a list of them. I'm gonna today cover the first half of it, pretty much. The L1 and L2 regularization, known penalties. After that, I'm gonna get into some math of L1 and L2 regularization, constraint optimization, and whatnot.
Hey, Shafaq, we do have a comment from the chat room that says your voice is not coming in very clear. Would you mind taking out the headphones and?
I'll do that then.
Yeah, awesome. Thank you so much.
How about now?
That's perfect. Thank you. That's great.
That's better, right?
Yes,
Okay.
way better.
I guess I will need to buy a new set of earphones. Okay. And then I'll talk about some dataset augmentation, some other exotic regularization schemes. And okay, the definition of regularization goes like this in the book. Regularization is any modification we make to a learning algorithm that's intended to reduce its test error, but not its training error. So we're not really concerned about the training error, but we definitely want to reduce the test error. On the x-axis, I put lambda, which is a regularization parameter. So if you increase lambda, your model is regularized more. And the test error comes down and scoops up in like a U shape. And this is like the sweet spot. This is, lambda is a hyperparameter. You find the sweet spot during your cross-validation phase of your learning algorithm. Next, and if you increase lambda indefinitely, then the training error increases. The bias will, let me see what happens. The bias will increase, the variance will drop too much, and the test error and train error will both explode. So what we're trying to do is find this sweet spot. Okay, L2 regularization. This is the most common form of regularization. It's also known as weight decay, or Tikhonov regularization, or ridge regression. Regularization increases the model bias, and it reduces the model variance, and that's our purpose in doing this. We covered bias and variance of models, in, I believe, in the chapter 5, in the machine learning basics chapter. So bias and variance is a property of your machine learning model. It is a measure of how sensitive your model is to your data set, because your data set is a random set. It's a random variable that you sample from your data producing probability distribution. And the purpose of regularization, and L2 regularization in this case, is to reduce the variance and increase the bias. Hence, we achieve this by adding this regularization term in the cost function. So JW here is the original unregularized cost function. It could be cross entropy. It could be a mean square error term, mean square error cost function. And by adding this regularization parameter in L2 is the excluding the bias term, which is important because we don't want to regularize the bias term. We want to keep the bias as it is and reduce the variance, which comes from the higher order weight parameters. And L2 regularization is defined by the square of the L2 norm of the weight vector, of the weight parameters. And alpha here, this 1/2 is just cosmetic, but alpha is something that we control. It's a hyperparameter. In the previous slide, I chose to call alpha lambda for whatever reason, but the book calls it alpha, so I use both symbols. So what happens here in this equation is, if the W weights, if some of them get too large, which means your model will be too sensitive to the training data, which also means it is going to have high variance. And in this objective function, when we add this regularization term, the large values of the weight parameters will be punished by this penalty. Rather, the objective function will be punished by this much. Hence, the objective function, we will learn to keep the weight parameters under control, the value of the weight parameters under control. So we will have like a smoother modeling function eventually. And the gradient descent update will be modified by this additional term. If you take the gradient of JReg, regularized, and set it to 0, this additional regularization term will contribute by this much. Half and 2 will cancel each other out, and we will have this linear term. Here, epsilon is the learning rate in your gradient descent routine, and alpha is your regularization parameter. Let's carry on. Okay, so this is a new thing that I've learned. L2 regularization has a direct connection with the constraint optimization. I believe we covered this in chapter 4. If you remember the constraint optimization equation, a constraint on an objective function that we're trying to optimize here is JW, prior to regularization. This regularization term is akin to having a constraint on this objective function. And this will be the constraint exactly. K is a constant that we don't explicitly set usually. We usually have the alpha as a hyperparameter. So indirectly, we control the value of k. And as alpha increases, k, I believe, will decrease, but I'll come to that in later slides. So for this case, this case, I'm in the constraint optimization view. We have an objective function that we're going to optimize, which is subject to this constraint. And here's the Lagrangian dual form equation. And this resembles the regularization objective function quite closely, except this k term. But when we're looking for, like in the gradient descent algorithm, when we're looking for the optimum point for JReg, we are basically taking the gradient and setting it to 0. So k is going to disappear there when we're looking for the gradient of objective function JReg with respect to the weights W. Carrying on to the next slide. This is, I always like, pictorial illustrations. It helps me understand the matters a little better. The Lagrangian constraint optimization basically works like this. Here are the solid contours. First of all, this figure is out of the deep learning book. I just added these additional vectors, the normal vectors, to hopefully drive it home. So what Lagrangian constraint optimization does is, here we have JW, which is the unconstrained, rather unregularized objective function. And in the center is where the gradient is 0. So this is the solution to our unregularized objective function. This is the optimum point. And when we add the regularization term, which is this term, we're basically constraining this JW by the constraint function, rather constraint term, the regularization term. And these blue vectors are the normals of the unregularized cost function and the regularization term. So the gradient of the J objective function is going to point outwards like that. And where they meet, the normals will be aligned. Just through geometry, you can just see that if the functions are smooth, at least in the first, smooth in the first derivative, at least, then the normals where they touch each other, where they are tangent, they're going to be on the same line. And the moduluses of these vectors is given by the Lagrange multiplier alpha, which happens to be our regularization parameter as well. Let me see if there's more anything more I need to describe here. So what I'm the gist of all this is, when you add the regularization term, setting an alpha, you are constraining the unregularized solution, the unregularized objective function, and the original solution, unregularized solution here, will be driven towards the origin. And how much that is going to be driven towards the origin is controlled by the Lagrangian multiplier, also known as the regularization parameter. And if we increase the regularization parameter for large alpha, the constraint region will shrink, and the solution will come closer to the origin like this. And yeah, I put it right here as well. I think this is all I'm going to say about this plot. Let me carry on. So there's a few other views of alto regularization besides Lagrangian constraint optimization. The book gets into the eigenvector analysis as well. It analyzes the cost function, the unregularized cost function, first of all, by expanding it in a Taylor series and taking the terms up to the second degree. So W star here is the unregularized solution for our unregularized cost function, and the Taylor series approximation is given by this. I think we went into this in the numerical computation chapter 4. And at WW star, the unregularized cost function, the gradient of the unregularized cost function J, is 0, because that's the solution to our objective function, the minimization of the objective function. And if you set it out, if you solve for the regularized, oh, wait a second. I shouldn't skip the important steps. So if you solve for the gradient of J and set it to 0, that's going to give you the solution for your minimization problem. And so basically you're solving for W star here, and this is what will come out.
We have a question from the chat room.
Please go ahead.
Someone asked, what's the H in the formula?
Oh, H is the Hessian. I should have put it there, maybe. H is the Hessian matrix of the cost function J at W star. So it's evaluated at W star, and this whole Taylor series approximation is based on the W star point, which is in the previous slide. It's right there. It's the solution to your unregularized objective minimization problem. So basically, we are expanding the J cost function, J of W, unregularized cost function, centered at this point. And the second degree basically consists of the Jacobian of the J function. Let me see, Jacobian. It's the gradient, rather, the gradient of the J function and the Hessian of the J function. So gradient is akin to the first derivative of J with respect to its arguments, and Hessian is the second derivative of J with respect to its arguments and cross derivatives as well. So if you solve for this, you can analytically solve for the regularized solution. Regularized means we have a non-zero alpha regularization parameter here. And this will hold exactly true for a linear regression case, because the linear regression objective function is a second order. It doesn't even have a third order. So the second order approximation will be exactly equal to the cost function. And this will hold exactly true for the linear regression case for any alpha that you will set as a regularization parameter. What we're trying to see is just to analyze this analytical expression for the regularized minimum solution for our regularized model. And H is a real symmetric matrix by definition. H of ij is equal to H of ji. And its eigenvector decomposition is going to be given like this. So V is made up of the eigenvectors. With each column resides another eigenvector of the Hessian matrix. And lambda is the eigenvalues, corresponding eigenvalues. And here we have the transpose because V is going to be an orthonormal matrix. So the inverse of it is going to be equal to transpose of it. So we have this nice expression for H, for the Hessian matrix. And when we solve for this, when we plug in the decomposition, eigenvector decomposition equation of Hessian matrix into the solution for the regularized weight vector, W star, this is what we're going to end up with. And we are just looking into this equation and trying to analyze, trying to see how the solution is going to change with respect to alpha. So the book makes a point that so this is an important one. Let me see if I'm going to be able to make it across. So H here, the Hessian matrix of this J, basically in two directions. In the horizontal direction, which is the W1 direction, the Hessian of the matrix is it's smaller compared to the vertical direction. So these are also its eigenvectors. For simplicity, the book has chosen an objective function whose eigenvectors are exactly aligned with the horizontal and the vertical axis. It could be tilted a little bit as well, but for simplicity, we're analyzing this simple J function. And in the small eigendirection, which is the horizontal direction, the weight will be affected more than in larger eigendirections. So this can be seen pictorially. W star has a W1 component and W2 component, and they pretty much are in the same level, in the same order. Let's say they're like about 5 or something. And in this case, as you see, the first W1 comes down to maybe like a fifth of the original solution, the original value. That's because, so that's the point that the book is trying to make. In the small eigendirection here is the W1 direction, the horizontal direction. The weight is affected more, it's regularized more, it's shrunk more than the W2 component of the weight vector. And it's exactly given, the stretch ratio is exactly given by this formula, lambda I being the eigen value in the ith eigendirection. And here is your hyperparameter alpha, the regularization parameter that you tune freely. So this is the point of this slide, the eigenvector analysis of the Hessian matrix of the unregularized cost function.
We have
moving on.
we
Yes.
have a few more questions in the chat.
Sure.
So Yogesh says, how did you go from H times W minus W asterisk equal to 0 to W times regularization equal to capitalized
Wait a
H?
second.
Yeah. You might have to just look at it.
Repeat that again? Oh, I have to look at it.
Well, either way, I can repeat
Good
it.
idea.
But yeah.
Oh, here. All right. Let me see.
Yes, yeah.
This one?
No, so the one above. How did you go from? Yeah. They're kind of asking the same question, I think.
Let me see. So how did I go from this one to W star reg to this one? Let's see how we went from there to there. Yeah, that's actually a good question. I might have skipped, for brevity, a couple of steps. I believe we introduced the regularization term in the objective function. To do that, how explicitly did we do that? We can't spend too much time on this right now.
Yeah, would you have to go through the proof in order to show it, or is there an easy way to explain it?
I can look into the book too. I usually, when I'm preparing for the presentations, I go through the derivations. And I don't necessarily put out like every single step on the slides. Just how it starts and how it ends. That's a fair question, though. I'm stalling. I'm so sorry.
No, you're fine. We appreciate you taking the time to do this and explain it to everyone as well. Obviously, you're volunteers, so it's it's great for you to be doing this for us. So yeah, we can, if you want to come back to the proof, we can definitely do that. Or
sure. I think it's a very subtle point, but I can't clearly see how the regularization term gets injected into the Taylor approximation. Yeah, I might, post it on the messages later on after the presentation.
Okay, that's perfect.
We can include that. Okay.
Yeah, we can include that in the additional resources for everyone, so it'll be a little bit more clear.
Fair.
Perfect.
Let me carry on with presenting another approach.
Oh, here, someone else said it's equation 7.8 in the book. So hopefully that's helpful.
Right, I was looking through that page. Yes, okay. We shouldn't spend too much time on this right now. We have a lot more to cover.
Not a problem. Thank you.
I really shouldn't be spending time. Okay, I'll probably post post it on messages on our meetup page after we're done with this presentation.
Thank you.
Okay, let me carry on with the normal equations for linear regression. So this is the normal equations, which is an explicit representation of the solution for our regularized and unregularized problems, linear regression problems. So if we set alpha equal to 0, that's our unregularized. I'm getting a little bit of a delay, Laura. I'm guessing it's from your end. Turn down the volume.
Everything seems fine here on my side.
Okay. Okay, never mind. So we are familiar with this normal equation in absence of the alpha I term right here, which is the additional term for the regularized case. So here the book is, just looking into this explicit equation for the solution of your regularized problem, regularized objective function, and trying to derive some insights. I enjoyed learning this, and let me quickly go over this. So with the regularization, we, if we go through the normal equations, starting with the regularized form, we'll end up with this additional term right here, alpha I added to the covariance term. The way to look at it is, so X is our design matrix for our linear regression problem, and Y are the labels from the training set. It's given. So X and Y are given. They entail the data set, the training data. And xty is basically, if you look at it, it's basically covariance of input features with the target values. So in this case, we have m by n design matrix. Let's think of this as 5 by 3. We have 5 points in 3 dimensions. We have 3 free features. And xty will be 3 by 1. It's going to be something like this. And each component, each entry of this vector will be the dot product of that feature with the target vector y. So the first component here is going to be this feature for all training for the data set, training data set with that. And xdx is proportional to the covariance of input features within one another. So xdx is a 3 by 3 matrix. And if you divide it by the number of data points, which is 5, and if you feature scale the training data, basically take the mean out of it, you will have the covariance matrix. So each entry will be either the variance of the feature within itself or the covariance with another neighboring feature. And we are adding some proportion of the identity matrix while we regularize the problem. So this is actually something super cool. This covariance matrix is being brought closer to the identity matrix by blowing up its diagonal values. This is what this additional term does. And eventually, this statement, I took it from the book. It says, L2 regularization causes the learning algorithm to perceive the input X with an increased variance, because we're increasing the values of the diagonals. And that's what regularization does. It stabilizes your problem. And if we have a small outcome for this xty, so I'm looking at xty term again. If, say, we have the first component smaller than the other two components, this term, the multiplier, this whole thing is just a matrix 3 by 3. And if you increase alpha, the regularization parameter, this whole sum is going to get closer to I, and if you inverse that I, it's going to be closer to I again. And which means it's just not even effective. So the extreme cases, this thing turns to I, and you invert it, you get I again, and then you omit it, and W is equal to that. Which means if the, which means if you have one of the components much smaller than the other components, the weight parameter corresponding to that dimension, to that direction, to that component rather, it's going to be small again. So, you know, in the end, what happens is when you regularize your problem, increasing alpha, that component weight, W1 in this case, will shrink more than the other components. I hope this is clear how I described it. And this is something I just, you know, learned this week when I was reading through the book, which I thought was pretty cool.
Yeah, this makes sense to me. As always, I think it's great if you can kind of relate it to something in the real world so that someone would understand when this would apply.
Yeah.
Do you have any examples?
No, I never thought of that. I can probably go to a simple canonical problem like you know, predicting the house prices or something, real estate value of a house. I mean, I just, you know, find the math of this beautiful. The book, you know, up to this chapter at least, is dwelling on the linear algebra and the foundations of machine learning basics, and just develops a new approach, or I shouldn't say new, just forces you to look at the equations and understand how they behave, just mathematically how they behave. Yeah, I think that's all I have to say about this.
Sure, go ahead.
Slide. The next one is L1 regularization. So I covered L2 regularization, I think, 4 different slides, and I just have one slide for L1 regularization. L1 regularization is also called LASSO. It's an acronym for something. And the regularization term, as opposed to the L2 term, is made of just the sum of the absolute values of the weight parameters. So this behaves very differently than in L2 regularization. The constraint optimization view is here on the right-hand side. I put it on the slide. I think I just modified one of the plots I saw on the book, in the book, and this is the constraint optimization view. In L2 norm, we had concentric. It's like a quadratic, like a two-dimensional parabola for L2 regularization. For L1 regularization, we have this like diamond-shaped contours. And the solution to your regularization problem happens when these two coincide at some given level prescribed by alpha, your regularization parameter. Hence, as you see here in this case, W1 is exactly equal to 0 because where they coincide, where they meet, is just one of the corners of that diamond shape, the constraint region. This is helpful to me personally. It helps me how I think of the regularization and makes the link with the constraint optimization. And okay, let me go through the math here. So this is our regularization term, omega of theta, theta being the weights. The book interchangeably uses theta and W for weights. And your regularization term, your regularization objective is given here. This is the L1. This is why this regularization is called L1. Because you're not squaring, but just taking the absolute value. So it's a summation of the linear terms of, made up of the weights, the components of the weight vector. And you set that to 0 to find a solution for your optimization problem. And you basically end up with just the sign of each weight component, as opposed to a linear term that comes out in the L2 regularization case. So this is qualitatively, this behaves different, qualitatively different than the L2 counterpart. And the book explains the same analysis we have done for L2 regularization, this time for L1, by expanding its Taylor series and taking the only the first 3 terms up to the 2nd degree. So for a linear regression, this is not approximately necessarily, but it's just exactly equal to that. And okay, so this ends up as a summation. The weight vectors, the weight components of the weight vector will end up as in a summation term. And each weight vector in the regularized minimization optimization solution is given by this formula. And so the second degree Taylor approximation ends up with this in the end. So each component of the weight vector is given by this. It either goes to 0 or it gets shifted by this amount, alpha divided by HII. So if that depends on these two conditions, here on the left-hand side, oops. If your WI star, which is the solution to the unregularized problem, is smaller than this amount by this fraction, then it's going to be sent to 0, basically. And otherwise, it's going to be shifted by this amount, alpha divided by HII. The takeaway from this analysis is the L1 regularization induces sparsity by sending some of the components of the weight vector directly to 0. So in some cases, this is a desired quality of the regularization because it is almost like feature selection. And here, I mean, if you look at the picture here, before you apply the L1 regularization, W1 and W2 are pretty much in the same level of magnitude, order of magnitude. And because of the Hessian matrix of the cost function, W1 is basically sent to 0 because the Hessian matrix in that direction, the second derivative rather of the objective function in that direction is much smaller compared to the other eigendirection. So it has some resemblances with the L2 regularization, certainly, but the outcome is qualitatively different than L2 regularization. The math of L2 regularization is, I think, a little more easy to deal with because you have, smooth functions in the end, and you can take derivatives and carry on with your analysis smoothly. Here you get these max functions and the conditions and whatnot in the analysis of L1 regularization. I mean, if you're going to remember one thing about lasso L1 regularization, it should be that it induces sparsity. It sends some of its likely to send some of the components of your weight vector directly to 0, exactly to 0. And the next section talks about the stability induced by regularization. For some problems, like under constraint problems, and as an example, I put up these two figures, plots for logistic regression. So in the left-hand side, this is a binary classification problem, and we're trying to solve it with logistic regression. And here, some of the red dots are your training data, and X is just your feature. You have one feature, and you're trying to separate these two classes with logistic regression. So here, around the same region for X, you have, so many, for small x, for instance, it's more likely that it belongs to the class 0 than class 1. But, every once in a while, you have some outliers, anomalies, and basically the data is not perfectly separable. And logistic regression behaves well under this case because logistic regression treats so the bold black line is the prediction of your model, and logistic regression, the prediction is interpreted as a probability, kind of like softmax. And it is trying to, through a cross-entropy loss, is trying to minimize this the probabilities, the misclassified probabilities. That's what the logistic regression does. It's trying to minimize the misclassified probabilities. So here, you have some misclassifications because the training data is kind of like intermingled with the opposing class. So in the same X region, you might get a lot of zeros, but every once in a while, you might have a couple class 1 data. And logistic regression works well with the linearly non-separable case by minimizing the probabilities, maximizing the likelihood rather, maximizing the probabilities. However, if we have a linearly separable case, this is what happens. If you run a gradient descent algorithm on a logistic regression on a linearly separable data set, at each gradient descent step, this model, the logistic regression function, which is defined by weights, will approach to something that looks like this. At every gradient step, it's going to get narrower and narrower because you're trying to increase the likelihood of your predictions. And since it's perfectly separable, all these red points will be your model is going to try to predict a perfect, like 100%, 1 out of 1 probability for these data points and 0 for these probabilities. So at each gradient descent, your W's, your weights, will be increasing. It's just going to be exploding indefinitely. So it's actually an underdetermined problem. So this is a good solution, but if you move your logistic regression function a little to the right, it's still going to be perfectly separating the data set, and it's still going to be a good solution. And your training error will be 0. So in order to circumvent this, if we introduce a little bit of a penalty, a norm penalty, a regularization term, we will constrain the magnitudes of the weights. Hence, the solution will not explode. It will settle somewhere in between, like this, but it's not going to have kind of like almost like a 90-degree. It's going to come out like that and then smoothen down, and then smooth here again. And the level of smoothing will be set by your regularization parameter alpha. So logistic regression, for instance, regularization induces some stability to your optimization routine. The next subsection, are there any questions, by the way? I haven't checked the chat window.
There haven't been any questions
All right.
since the last one. Yeah, so you're good.
Okay, I have a few more slides. Yes. So the next subsection talks about data augmentation. I think most of the math was contained until this point. And from now on, it talks qualitatively about some regularization strategies. For instance, the data augmentation works really well for object recognition tasks, for coordinates, for instance. And here, the first bullet, let me read it through. So the best way, it says, to improve the generalization of a model, which is the purpose of the regularization, is to improve the generalization and not care too much about the training error. Improved generalization of a model is to train it on more data. So data is actually the best regularizer. If you have a lot of data, then you won't need to regularize your model as much, at least. And one classic strategy to tackle object recognition tasks with convolutional networks, for instance, is to augment your data through some of these processes, which is listed here, like for an input data. So what you do is for each input data, you increase your data set by maybe affine distortions, applying some noise. I don't know if you can see, this is the original data. Here it's smooth, and here it's a little noisy, adding a little noise. And when you add a little noise, you're basically getting a new data point with the same label. This is still a butterfly class. You could be deforming the image slightly, or flipping it. It's still the same label. If you look at the butterfly, flip it around. You can translate it. All these, or change the color slightly. So all these additional data points are legitimate data points in your data set, and they just fill out your input data manifold. Basically, that's what you're trying to do. You're trying to increase the density of your manifold, so your model will be able to learn the distribution of your data set and learn the distribution of your manifold, better. For speech recognition, injecting noise into the audio signals is another commonly used strategy to augment your data. Next slide is the next section, talks about the noise robustness a little bit. So the addition of noise with a small variance is equivalent to imposing norm penalty on weights. So that's the premise. Neural networks
Can you describe,
yeah.
Shafaq, can you describe what is norm penalty exactly?
Oh, norm penalty is just the regularization term.
Mm-hmm.
I might have skipped that. I mean, in statistics and machine learning field, we, in different academic communities like to use different terms. Like for L2, I'm looking for the slide. So, L2 regularization can be called weight decay or ridge regression. And it's basically this, the second term, the regularization term. This is a norm penalty. You're penalizing your objective function here if it attains large values for your weight vector, or the components in your weight vector. So this is called a norm because this is the norm of your weight vector. Actually, it's squared of the norm. So when you talk about norm penalty, you're talking about L1 or L2 regularization.
Thank you. And we also have another question from the chat room that says, why does more data improve generalization? Please elaborate.
Why does more data improve generalization? Mm-hmm. Because it goes back to this bias and variance analysis. I don't have any slide to go over that right now, but I can talk about it.
Sure.
So the data set is a random variable on its own, because each time you generate a set of data, let's talk about like 10 points, 10 data points. Those collection of 10 data points is a random variable on its own. If you collect another 10 data points on top of the first 10, it will be another collection of 10 data points. And if you fit, so you have, assume you have two separate data sets of 10, size 10 each. And if you fit your machine learning model on the first data set, you will get some function out of it without any regularization. And you do the same thing for your second data set, another set of 10 data points. You will get another model. And those two models will not be the same because they are dependent on your data set, which is a random variable. So the model that you found through your optimization routine is a function of a random variable, which is the data set. So since it is dependent on a random variable, it is a random variable itself. And since it's a random variable, we can talk about its expectation, and we can talk about its variance and its statistical properties. So this is the model bias and model variance. It's a very important concept. And if you increase the number of data points, you will make your machine learning model less susceptible to the incoming data set. That can be given by, what's that called? Sampling, like the sampling theorem. The variance of a sample is given by what was it? It was sigma divided by square root of n being the size of your sample. So if you increase n, the variance of your sample, or rather the standard error, which is the variance of the expected value of your sample, is going to be proportional to the number of data points n. Well, it's 1 over square root of the number of data points n. I hope you were able to follow me without any help from the visuals. But basically, if you increase the data set, it will be more robust. Its statistical properties will be more steady. But if you're talking about a small data set, then depending on which data points you generated from your data generating distribution, your model will be very sensitive and will likely overfit. So if you have a lot of data, which what the data augmentation process does, if you have a lot of data, then your model will be more robust and will have less of a variance. It's not going to vary too much depending on your data set. I hope that was helpful.
I think it was, definitely.
Okay.
Yeah.
Let me carry on with the noise robustness concept. And we will have to wrap up pretty soon. In 5 or 10 minutes, I guess. That's all I have. The addition of noise with a small variance is equivalent to imposing norm penalty on weights. That's where I left off, right? So norm penalty is another term for the regularization term. It's just another wording. And there's another exotic concept, which is adding noise on weights. So for each data set, let me see how it works. So for, we can consider another linear regression setting for simplicity. We are trying to train a function y hat. And here is the y hat, and it is going to map this features x to a scalar label y using the least squares optimization, least squares cost function. And the training set, let's assume we have like a training set of m data points. And we can now assume with each input, there's a random noise on top of the the model function y hat, the estimator. So for each input data, we apply this noise. So we jiggle the weights around a little bit. And the purpose of this is to force the machine learning model, the optimization routine, to be more robust to this jiggle action. And typically we choose the jiggle to be, the epsilon noise to be distributed normally. I think I made a mistake. This is not x, but this should be 0 with 0 mean. I should correct that after the talk is done. With 0 mean and the small sigma variance of noise. And if you walk through the whole optimization routine, the cost function will be modified by this. Basically, y hat, we're adding an epsilon next to that y hat, and this will be our cost function that we need to optimize. And the book doesn't really work out the details, how it arrives at this from this. But this eta, see, I made a mistake. This sigma and eta are actually the same thing. This is the variance of the noise. I like to use sigma. The book used eta. So the regularization term. So basically, if you work out the math here, you'll end up with an additional term caused by the noise, and this will be acting like a regularization term to your objective in your objective function. So I mean, basically, what's happening is conceptually, to reiterate myself, the noise that you impose, the small amount of noise that you impose on the weights, acts like a level of uncertainty on your weights. So you're trying to, I mean, there's some Bayesian approach to this too. In Bayesian statistics versus frequentist statistics, in Bayesian statistics, we treat the unknown parameters to be uncertain and to be represented by a probability distribution. So this epsilon basically is another kind of like a Monte Carlo simulation in this way. We're trying to model this uncertainty by a small perturbation, because otherwise we're in the frequentist realm, frequentist approach, and the unknown vector, the unknown weight vector, we treat them as unknown but some fixed value, and by jiggling them by an amount of epsilon, we are kind of like running Monte Carlo-esque simulation over the Bayesian, over the weights, as dictated by the Bayesian approach. I mean, in the end, if you run through the math, you end up with an additional term which scales with the standard deviation of the Gaussian noise, eta. And this basically acts like that constraint term or regularization term in your objective function.
Hey, Shafak, we had a few more comments and questions in the chat room. Okay. I didn't want to interrupt you until you were done with that portion. But I don't know if you want to switch over there. So the first one was that someone, Yogesh, says, it's probably approximately correct, might also help explain why more data helps in machine learning.
Yogesh, where I can see it. Oh, here, Yogesh Luthra. Basically, more data helps to eliminate incorrect hypotheses with higher probability. I can't really make out what he's trying to say. More data helps to eliminate incorrect hypotheses. would it be fair to say that incorrect hypothesis? Your hypothesis function doesn't need to be incorrect. I mean, hypothesis is just a family of functions. It's like a quadratic function. If you include a quadratic term in your linear regression, or a cube term, so you have higher order terms, polynomial terms, in your hypothesis. And your model can have that. You know, intrinsically, it might behave in a quadratic or cubic way. And if you don't have too much regularization, and if your data set is small, then you are likely to overfit on the noise that comes with your data that you can't help. But that doesn't mean your hypothesis was wrong. Your problem can still have a quadratic pattern underneath, but your data, since your data is, you know, limited, you might not be able to represent that pattern in your data, in your data, right? And yeah, I mean, I beg to differ there. It doesn't need to be incorrect. Maybe the wording could be changed. It basically decreases the variance. That's what regularization does. I'm going to a lot of math because I'm covering the book, but regularization is basically a tool to decrease the model variance while keeping the bias unchanged or, you know, increased by a little bit, by trying to not touch the bias too much. So the regularization term in L1 and L2 regularization, you exclude the bias term in your weight vector and regularize only on the higher order terms, which are responsible for overfitting. So this is, I think, regularization in a nutshell. It's a tool to decrease model variance. There's more things coming in. Should I carry on? There's like 2 more slides. Let me finish that.
Yeah.
Okay.
Come back to the chat room.
Sure. So I think this will be quick. This early stopping, you might have heard about this. You can move ahead a little bit. So this is the, what's this called? This is the error, you know, MSE, mean squared error, in your gradient descent algorithm. MSE, or cross entropy loss, you know, in general, is the loss or negative log likelihood. So the blue is the training loss, and the jiggly green solid line is the validation or test loss, the loss on your test set. So as you are learning, the training loss is coming down. And because your model is explaining the variance better and better with every epoch of your gradient descent. And if you concurrently test your model with the weights at that particular time step, gradient descent step, you can plot the green line and the blue line concurrently at each time step as your model is going under that gradient descent routine, your objective function rather. And at some point, you will start to overfit if your model capacity is higher than the problem's intrinsic model. Oh my God, decline. I'm sorry about that. So okay, where was I? So here, if you learn your training dataset too much, you start to learn the noise as well. And at that point, you know, your weights will be arranged in such a way that it is explaining the noise on your training dataset. And this is not good for the validation loss, because if you use those weights to calculate the validation set loss, you will see that with each epoch, the validation set loss will increase because your pattern, your model, will be explaining something just particular to your training data set, but not to the general case that's represented by your validation set or test set. So this is why overtraining can result in an overfit. And I like to think about things on plots. I like to think graphically, much like Newton did. In his book, everything he says, there's always a plot, some triangles and whatnot. Maybe it's a habit of physicists. So basically what early stopping is, graphically, it's kind of like that. So here we start with on the origin, or somewhere around the origin, with very small initial guesses for the weight vectors. And you're training the weight vectors, right? That's what gradient descent does. And with each set, you're moving in the gradient direction of your objective function, right? Actually, I can, let me do this. This is your gradient descent update rule. I'm going to copy this and bring it over here. So this is the gradient descent update rule. And so each step, epsilon here is the learning rate, and alpha is your regularization parameter. With each step, you're moving in the gradient j direction by epsilon much, by the amount dictated by the learning rate. So here, when you start out first, the gradient of j is large because you're so far from the bottom of that well. And the initial steps will be larger. It's going to be taking larger strides at first. And as you take tau many steps, you move from the 0, 0, the origin, to somewhere around there. And you're always moving, so this is the key point, you're always moving in the gradient j direction, which is the normal to the contours of j. So here, at this point, if you take a gradient step stride, it's gonna be moving in this direction. And then you land here, and then you calculate the gradient of j again, and then that direction is gonna be, shifted a little, angle towards, the origin here, not the origin, the W star, let's call it. So we have no regularization parameter here. We have the pure unregularized cost function j. But what we can do is, if we don't run the regularization, the optimization routine to oblivion, basically, here, it's coming down to 0. You're just starting to get closer and closer to that W star, the ultimate point where the gradient of j is exactly equal to 0. If we stop, before we get there, what happens is, equivalently, we are basically performing an L2 regularization. Because if you stop there, you basically have stopped at a point where the gradient of j is aligned with the gradient of the L2 term. It's like this. I'm going back to this former slide. So if you stop here, you're basically stopping at the location where the normal vectors of the gradient of the contours of the unregularized cost function j and the regularization term, the L2 regularization term, W norm squared equals some constant k, will be aligned. And that is the solution to your constraint optimization. That is the solution to a certain level alpha of your regularized objective function. So this is actually a pretty clever way. You don't have to go through the modification in your objective function and embedding that gradient of your regularization term into the optimization routine. You don't have to do any of those. This is, I mean, you can't really explicitly control epsilon, rather alpha, not epsilon, the regularization parameter alpha, because you don't exactly know when you stopped what alpha it corresponds to, but there is a some measure of what alpha is at a given time step in your gradient descent routine, which is, if you work out the math, which is done in the book, it basically scales like this. Alpha, the unknown alpha, scales as 1 over epsilon times tau, given that the learning rate is small. Because if you're like shooting around the walls, like we saw in previous chapters, that's not what you would be doing. But if the epsilon is small, so you're continuously going in the gradient direction, the gradient of the objective function direction, so it's moving nice and smoothly towards the W star value. You can do this in neural networks, training your neural networks. So basically this happens in deep learning, in neural networks. You have so many parameters, your neural network is actually a very, very high variance model. It's very flexible. You give it a little bit of data, it memorizes that data immediately, which means it's not good. It's memorizing the training data. Memorizing means overfitting and poor generalization. So what you could do is not worry about the regularization too much, but try to increase your data set by augmentation or collecting more data, and also early stopping during your stochastic gradient descent routine. So you don't learn more than you should. You don't learn the noise that comes with your training data. So this is all I'm gonna, this is all I'm gonna say about
Thank you,
the first
Shafak.
half of the chapter 7. Yes.
Yeah, we do have a few more questions that were brought up in the chat if you would like to address them.
Sure.
Yep, so we had a few from before and then also a few more that have been added. So let's see, let's go back. I'm not sure where you left off. We've got, so Pankaj said data augmentation, he doesn't think increases the data points so much to better cover the full volume of increased dimension. I think that was referring to someone else's question.
I think it does though.
You think
I think that's the whole premise of data augmentation. Yeah. So data augmentation, let's go back to that butterfly picture. So this is one point in your super high dimensional feature space, right? If this is 100 by 100 image, 100 pixels by 100 pixels, that gives you what, 10,000 dimensions in your input? This is just one point in that 10,000 dimensional feature space. This is a butterfly. That's the label of that point. And the location of that point is given by the pixel values of this picture. If you shift this, random translation, for instance, if you shift this butterfly a little bit off to the side, this is going to take you to another point in your 10,000 dimensional feature space. A second point which has the same label, because as a human, you can look at this picture and you can label it with confidence that it's a butterfly. And you can add some noise. You can deform it a little bit. It still looks like a butterfly, and you want your model, your neural network model, to label this as butterfly, to learn to label it as being a butterfly. So what happened is you start with one data point, and then you shift the picture, you flip it, you add some noise, or you add some red hue or yellowish hue to it. Anything you do to the input image will make you end up in another data point another point in your 10,000 dimensional feature space. But these points are kind of close to one another. They still reside in that little manifold. So essentially, where was that? Essentially, the data augmentation strategy increases the number of data points and fills up your manifold. So your machine learning model can detect that manifold better and learn the distribution of that manifold better. Of course, this comes with a cost. You have more data, so you will need stronger machines to train your model on.
Great, thank you. And then we have, so Abdullah says you called it test set and the slide says it's a validation set. So what's the difference between them if we already know we have to use training, validation, and testing sets? Yeah.
Validation test sets, they are used interchangeably, but they actually refer to separate things, separate parts of your data. So test set, so we have 3 different sets, right? We have a whole bunch of data points, and then we take only 65% of it, and we use it as a training set. So this blue curve is calculated, is plotted by training your model on the first 65% of your data set. And another 15% will be used to tune your hyperparameters, which is called the validation set. So that 15% is what gives you this solid green line. And the remaining 20% will be a test set, which is only going to be used to assess your model accuracy. So it doesn't have any influence on the training. You don't use that test set to choose your hyperparameters or the architecture of your neural network. If you want to make a decision on how many hidden layers you want to use or how your dropout layers should be configured, you're going to do that on that 15% validation set. So validation is basically a test as well. But it's a test not for computing the accuracy or the performance of your model, but that is used to tune your hyperparameters and make decisions on the architecture of your neural network model or machine learning model. So I have used that interchangeably, but I think the proper way to call it is the validation set. Because you would never plot anything like this on your test set. Test set is something, you just take out the 20% chunk in your incoming data set and then you put it away. You don't touch it until you develop your model. You run all these tests and analysis, and then you don't touch it until the very end. Like in Kaggle competitions, you don't even see the test set. You just send it to the server once you develop your model, and then it runs it and then spits out some accuracy level. So that's the test set. Next question, if there are any more questions.
Yeah, so it said, so this is from Jay Jashim again. Presenter said regularization reduces variance, keeping bias untouched. Does it mean even ensemble can be called as regularizer method, as ensemble aids to reduce variance, keeping bias constant?
Okay, wait a second. I missed it. Are we looking at this?
No. 2 above that one. 2
above this one.
From Jay Jashim. Yeah.
Presenter said regularization reduces variance, keeping bias untouched. Yeah, I shouldn't say untouched, but you're trying to not touch it. Yeah, that's the. That's what you're trying to do. You're not trying to regularize the bias, just the variance. But you might affect the bias as well, unintentionally. Does it mean even ensemble can be called this regularizer method? Is ensemble aids to reduce variance, keeping bias constant? This is an excellent point. Let me think about that. Yes, I thought about it. The answer is yes. Actually, when you do ensemble methods on decision trees, for instance, decision trees are non-parametric models. They don't have weights that you form an objective function as a function of, and then set the gradient to 0 and yada yada yada. You don't have weights. You have branches and depth of the tree, and the decision trees are kind of like neural network models are high variance models. They are known to overfit on your training data set very easily. And to circumvent that, you use ensemble methods and boosting. Ensemble methods basically does what regularization does for what neural networks and linear regression and whatnot. It's typically L1 and L2 regularization I'm talking about. So for decision trees, you don't have L1, L2 regularization because you don't have weights, right? So you do use ensemble averaging. So you take some part of your training set and you feed it into one decision tree, and then you form a decision tree model based on that part of your training data set. And then you have another decision tree. You just repeat that 10 times or 100 times, and then you average all of them. So that averaging actually basically averages over the noise, which cancels out that whole overfitting phenomena. It cancels out that noise. So yeah, exactly. That's a great point, Jay Jashin.
Thank you. Okay, so it looks like otherwise we had a couple of just statements. Yeah, so it looks like that was the last actual question that people asked. So we do want to thank you again for your time, Shafak. So just to remind everyone, so this was only half of this chapter, chapter 7. Yeah. We'll be covering the other half of chapter 7 next Saturday. Online, and that will start with the semi-supervised learning and go through tangent distance and manifold tangent classifiers. And for those that are in the San Francisco area, we also have meetups in person. So if you're part of our meetup group, the Deep Learning Enthusiasts Online, you can come hang out with us on Thursdays, where we're covering deep reinforcement learning, currently by Berkeley. That happens at Dev Bootcamp in San Francisco. And then we also have Monday meetups where we're also covering the deep learning book, and it's a very similar format to this, that we have presenters show up and volunteer for us each week. And that was also happening bi-weekly. We are now moving it to weekly to help, again, facilitate more learning and going more in depth into this material, since it's getting very dense. We want to make sure everyone covers all the topics as well as possible. Guys for joining us, and thanks again to our presenters. If you would like to volunteer to be a presenter, we do have that spreadsheet set up linked here in the YouTube channel and also on our meetup page. And so if you'll see, there are 2 tabs at the bottom on the spreadsheet, one that says online, another that says San Francisco. If you'd like to volunteer for the online session, please put your name and email address, and then I'll follow up with you in order to get that set up. If you'd like to volunteer for the San Francisco session, you can also do that by clicking on that tab and putting in your name and email address, and we will see you there as well. And so again, just to give people some clarification, these presentations can be as short as 10 minutes, although they never are, as long as an hour or 2 hours. And of course, we like if you do prepare your own slides, you don't have to. The Deep Learning book online actually comes with slides given by the authors. So, which is very nice of them to do as well. So you could utilize theirs if you would like, or you could just use like a paint program and just draw out the calculations if you would prefer to do that. So thanks everyone for joining us. Again, we have people joining us in from all over the world on these online sessions, so we're really grateful for that. We really want to create this community learning experience and have people really grow and understand deep learning better. So thanks everyone for joining us, and we'll be signing off. Weekend.
All right, thanks so much.